ladies and gentlemen, esteemed guests, and fellow enthusiasts of engineering marvels. Today, I am honored to delve into the intricate and fascinating world of clock engineering. Clocks have been an integral part of human civilization for centuries, serving not only as timekeepers but as symbols of human ingenuity and precision. Engineering behind clocks is a testament to our relentless pursuit of measuring and mastering time, and it has evolved over millennia into an art and science of unparalleled complexity. Generally, clocks, whether they are traditional mechanical pendulum clocks or modern digital timepieces, are fundamentally governed by the laws of physics. In the case of traditional pendulum clocks, the physics of oscillations takes center stage. The pendulum, a suspended weight, swings back and forth under the influence of gravity. This movement adheres to the principles of simple harmonic motion, characterized by a constant period of oscillation, which means that the time it takes for the pendulum to complete one full swing is determined solely by the length of the pendulum and the strength of gravity in that location. Another crucial element of clock physics is the escapement mechanism. This mechanism regulates the release of energy from a wound spring or a falling weight into the clock's gears. It operates on the principle of periodic impulses, allowing the clock's gear train to advance at a constant rate. The escapement ensures that the clock's hands move in discrete, regular increments, thereby marking the passage of time with precision. In spring-driven clocks, such as many vintage timepieces, potential energy plays a pivotal role. These clocks rely on a tightly coiled spring as their primary energy source. As the spring unwinds, it releases its stored potential energy, which is then transferred through the gear train to drive the clock's hands. The rate at which the spring unwinds is meticulously controlled, ensuring the clock's accuracy over time. The clock's gear train and the mechanical advantage it provides are also vital aspects of clock physics. Clocks use a complex system of gears and wheels, each with a specific number of teeth, to divide time into precise intervals. The manipulation of gear ratios allows clockmakers to control the speed at which various components of the clock move, thus ensuring the accuracy of timekeeping. Moreover, energy transfer and friction are significant considerations in clock mechanisms. Efficient energy transfer is essential to ensure that energy from the mainspring or weight is transmitted effectively through the gear train. Minimizing friction, both in the bearings and between gear teeth, is critical for maintaining the clock's accuracy and longevity. Materials science plays a role in clock engineering as well. Clockmakers choose materials like brass and steel for their durability and resistance to temperature changes. Understanding the coefficient of thermal expansion of these materials helps minimize the impact of temperature variations on clock accuracy. In modern clocks, especially those used in digital displays, electromagnetism and semiconductor physics are paramount. Quartz crystals, for example, exhibit a precise and consistent vibrational frequency when subjected to an electric current, making them ideal as oscillators for quartz clocks. Digital clocks rely on electronic components and microprocessors that manipulate electric signals to display time accurately. Overall, clocks are intricate devices that encompass a broad range of physics principles, from the mechanics of oscillations and gear systems to the transfer of energy and materials science considerations. They represent a fascinating fusion of classical and modern physics, underscoring their role not only as practical timekeeping instruments but also as remarkable manifestations of human scientific and engineering ingenuity. But, let us embark on this journey through time, exploring the engineering marvels that have shaped our understanding of the passing hours and minutes. Clocks have a rich history dating back to ancient civilizations. Early timekeeping devices, such as sundials and water clocks, laid the foundation for more complex mechanisms. The concept of dividing time into hours, minutes, and seconds was revolutionary, requiring intricate engineering. The story of clocks begins with the earliest human civilizations, where the need to measure time was of paramount importance. As we look back into history, we find remarkable examples of ingenuity in early timekeeping devices. Sundials, for instance, were among the earliest timekeepers used by civilizations like the Egyptians, Greeks, and Romans. These devices relied on the position of the sun's shadow cast upon a marked surface to indicate the time of day. Sundials not only provided a practical means to tell time but also demonstrated a profound understanding of celestial movements. Water clocks, or clepsydra, were another remarkable invention, employed by ancient civilizations like the Babylonians and Chinese. Water clocks operated on the principle of regulating the flow of water from one container to another. The gradual filling or emptying of a vessel allowed people to approximate the passage of time. These early timekeeping devices were instrumental in activities ranging from agricultural planning to religious ceremonies. However, it was the conceptual leap of dividing time into hours, minutes, and seconds that truly marked a revolutionary moment in the history of clock engineering. The realization that time could be systematically organized into smaller, measurable units demanded not only mathematical precision but also intricate mechanical design. This innovation laid the foundation for the development of more sophisticated timekeeping instruments, ultimately leading to the creation of mechanical clocks. The transition from sundials and water clocks to mechanical clocks was a pivotal moment in the history of timekeeping. These early mechanical clocks, which emerged during the medieval period in Europe, were intricate marvels of engineering. They employed gear systems, weights, and escapement mechanisms to regulate the flow of energy and maintain consistent timekeeping. These clocks found their way into monasteries, town squares, and eventually private homes, shaping the daily routines of societies and enabling synchronization of activities. In essence, the engineering behind early clocks transformed the way humans interacted with time. It allowed for more precise scheduling of tasks, better organization of work, and the evolution of societies into more structured and efficient entities. The concept of dividing time into hours, minutes, and seconds, which began as a revolutionary idea in ancient civilizations, has become an integral part of our daily lives, thanks to the intricate and visionary engineering that brought these ideas to life. This rich history of timekeeping devices is a testament to humanity's eternal quest to master time and to create instruments that resonate with both artistic beauty and scientific precision. One of the most critical developments in clock engineering was the invention of the escapement mechanism. This ingenious invention, attributed to various inventors throughout history, including Galileo and Huygens, made precise timekeeping possible. The escapement regulates the release of energy from a wound spring or falling weight, allowing the clock to tick at a constant rate. The invention of the escapement mechanism marked a profound turning point in the history of timekeeping. Before its development, early clocks lacked the precision required for accurate time measurement. These early timekeepers, including sundials and water clocks, were inconsistent, relying on natural phenomena like the sun's position or the flow of water. The concept of dividing time into equal intervals was a daunting challenge for clockmakers of the time. The escapement, often attributed to various inventors including Galileo Galilei and Christine Huygens, brought about a transformative breakthrough. It introduced a method to control the release of energy from a clock's power source, whether it was a wound spring or a falling weight. This control was achieved by employing a set of interlocking gears and levers. The escapement mechanism essentially acts as a brake, allowing the energy source to advance the clock's gear train at a precisely regulated rate. When the escapement releases a tooth of the gear, it produces the familiar tick that we associate with mechanical clocks. The escapement's ingenious design ensures that each tick of the clock corresponds to a consistent interval of time, creating the basis for accurate and reliable timekeeping. Furthermore, escapements are designed with incredible precision, often involving intricate calculations to determine the size and shape of the escapement wheel's teeth and pallets. These considerations are crucial in ensuring that the escapement operates with minimal friction and wear. contributing to the clock's longevity and accuracy. The escapement's influence extended far beyond traditional mechanical clocks. It became a fundamental component in various timekeeping devices, including pendulum clocks, pocket watches, and even early marine chronometers. Its role in regulating time allowed clockmakers to explore new levels of accuracy and reliability. The escapement mechanism is a testament to the ingenuity of clock engineers throughout history. Its development revolutionized timekeeping, making it possible to measure time with unparalleled precision. This mechanical marvel is not only a crucial component in traditional timepieces but also a symbol of our quest for accuracy and the enduring legacy of human innovation in the field of engineering. It laid the foundation for the intricate mechanisms that power the clocks we rely on today, demonstrating how a seemingly simple invention can have a profound impact on our understanding of time. In the 17th century, Christine Huygens introduced the pendulum clock, a groundbreaking development. The pendulum's natural harmonic motion allowed for unprecedented accuracy. The engineering behind pendulum clocks involved precise calculations of pendulum length and weight to achieve consistent oscillations. In the 17th century, the introduction of the pendulum clock by the Dutch scientist and inventor Christine Huygens marked a watershed moment in the history of timekeeping. Huygens' breakthrough was rooted in his deep understanding of physics and mathematics, particularly the principles of oscillation and harmonic motion. The pendulum, a simple yet elegant device, was central to this innovation. The pendulum's natural harmonic motion was critical to achieving the clock's unprecedented accuracy. It swings back and forth in a regular, predictable pattern, known as an isochronous motion. This inherent property of the pendulum made it an ideal timekeeping element, as its oscillations remained nearly constant regardless of the amplitude or width of the swing. This constancy was crucial for achieving precise timekeeping, as it minimized errors in time measurement. The engineering behind pendulum clocks involved meticulous calculations of the pendulum's length and weight. The length of the pendulum, in particular, was meticulously determined to achieve consistent oscillations. The formula for the period of a simple pendulum, T equals 2I diaresis L/G, where T represents the time for one complete swing, L is the length of the pendulum, and G is the acceleration due to gravity, became fundamental to clock design. Clockmakers had to ensure that the pendulum's length was precisely calibrated to the desired timekeeping accuracy. Even slight variations in the length could result in significant timekeeping errors. This required craftsmanship of the highest order, as clockmakers carefully measured and adjusted the pendulum length to achieve the utmost accuracy. Furthermore, Huygens' pendulum clock also incorporated a unique escapement mechanism, which allowed for the controlled release of energy from a wound spring or falling weight. The escapement provided the periodic impulses necessary to keep the pendulum oscillating and ensure the clock's regular timekeeping. In essence, the engineering of pendulum clocks was a fusion of physics, mathematics, and craftsmanship. It represented a remarkable marriage of scientific understanding and practical design. Huygens' invention not only revolutionized timekeeping but also laid the foundation for future developments in horology, inspiring generations of clockmakers and engineers to push the boundaries of precision and accuracy in measuring time. The pendulum clock stands as a testament to human ingenuity and remains an enduring symbol of our quest for ever more accurate timekeeping. Clockmakers later transitioned to spring-driven mechanisms, eliminating the need for hanging weights. The mainspring stores energy, released in a controlled manner through the escapement. The creation of miniaturized, high-tension springs demanded precision engineering skills. The development of spring-driven clocks was a monumental leap in the evolution of timekeeping technology. Prior to their introduction, mechanical clocks relied on the force of gravity, with heavy weights suspended from pulleys or chains to provide the energy needed for consistent operation. This design had its limitations, as it required substantial space and often led to large, bulky clock towers. The emergence of spring-driven mechanisms in the late 15th century, notably during the Renaissance period, revolutionized the field of clockmaking. At the heart of this innovation was the mainspring, a tightly wound coil of steel or other materials capable of storing mechanical energy. The mainspring served as the power source for the clock, replacing the cumbersome weights. This compact and efficient energy storage device allowed for the creation of smaller, more portable timepieces, including the early pocket watches. The mainspring was wound using a key or a knob, storing potential energy that would be gradually released to drive the clock's movement. However, harnessing the energy of a mainspring required precise engineering, particularly in the design of the escapement mechanism. The escapement acted as a control mechanism, governing the release of energy from the mainspring in a controlled, regulated manner. It ensured that the clock's gears and hands moved at a consistent rate, making accurate timekeeping possible. To achieve this precision, clockmakers had to master the art of creating high-tension, miniaturized springs that could store sufficient energy to power the clock while also ensuring that the escapement allowed for uniform, incremental release of that energy. This was no small feat, as it required a deep understanding of materials, geometry, and mechanics. In the hands of skilled clockmakers and watchmakers, spring-driven mechanisms ushered in a new era of timekeeping that combined precision with portability. Clocks and watches became not only functional timekeeping devices but also intricate pieces of craftsmanship, with beautifully designed cases and intricate movements. The transition to spring-driven mechanisms was not only a technological advancement but also a cultural shift. Clocks and watches became status symbols and pieces of art, showcasing the mastery of engineering and craftsmanship. They played a crucial role in shaping society, impacting everything from business and transportation to personal punctuality and the synchronization of daily life. The shift from weight-driven to spring-driven mechanisms in clock engineering was a transformative moment in horological history. It allowed for the creation of smaller, more portable timekeeping devices, expanded their accessibility, and drove the development of precision engineering skills. This transition laid the foundation for the intricate and finely tuned timepieces we admire today, and it reflects the indomitable human spirit of innovation and progress. The Industrial Revolution marked a significant turning point in clock engineering. Mass production techniques, powered by steam engines and later electricity, made clocks more accessible to the general public. Innovations in materials, such as brass and steel, enabled the creation of intricate clockworks. The Industrial Revolution, which began in the late 18th century and extended into the 19th century, brought about a seismic shift in manufacturing processes across various industries, including clockmaking. It marked a transformative era when traditional craftsmanship gave way to mechanization and mass production techniques, powered by steam engines and, later on, electricity. This transition had a profound impact on the world of clocks. One of the most significant advancements during this period was the adoption of standardized manufacturing processes. Prior to the Industrial Revolution, clockmakers crafted timepieces by hand, which was a labor-intensive and time-consuming endeavor. Each clock was a unique piece of artistry, but it also meant that clocks were prohibitively expensive and rare. With the advent of mass production techniques, clock components could be manufactured to consistent and precise standards. This standardization made it possible to create interchangeable parts, significantly reducing the cost of production and making clocks more affordable to the general public. This democratization of timekeeping meant that people from all walks of life could now own a reliable clock, enhancing their ability to manage their daily schedules and activities with greater precision. Innovations in materials also played a crucial role in advancing clock engineering during the Industrial Revolution. Clockmakers began using materials such as brass and steel, which were readily available and could be machined with greater precision than traditional materials like wood. Brass and steel were not only durable but also resistant to temperature changes and corrosion, ensuring the longevity and accuracy of the clockworks. These innovations enabled the creation of intricate and finely tuned clock mechanisms that could maintain accurate time over extended periods. The Industrial Revolution marked a transformative period in clock engineering. The shift from handcrafted, artisanal clocks to mass-produced, standardized timepieces made clocks accessible to a wider audience. This accessibility, combined with innovations in materials and manufacturing processes, paved the way for the modern clock industry, making accurate timekeeping an essential part of everyday life for people around the world. The legacy of this era can still be seen in the clocks we use today, which owe their affordability, precision, and accessibility to the engineering innovations of the Industrial Revolution. The quest for precise timekeeping was crucial for maritime navigation. John Harrison's invention of the marine chronometer in the 18th century was a pinnacle of engineering achievement. These devices maintained accuracy even in the harshest conditions, allowing sailors to determine their longitudinal position with unprecedented precision. The age of exploration was a time of great maritime adventure and discovery, as seafarers from Europe and other parts of the world embarked on lengthy voyages to explore uncharted territories. However, navigating the vast and often treacherous oceans posed a formidable challenge. While latitude, north-south position, could be determined relatively accurately using celestial observations like the altitude of the sun or the stars above the horizon, longitudinal position, east-west, remained an enigma. Determining longitude was essential for sailors to accurately plot their course and avoid disastrous navigational errors. Before John Harrison's invention, sailors had to rely on imprecise methods, such as dead reckoning or estimating distances traveled based on speed and direction, which often led to costly mistakes. John Harrison, a self-taught English carpenter and clockmaker, recognized the urgent need for a solution. In the mid-18th century, he embarked on the quest to create a timekeeping instrument that could maintain exceptional accuracy, even in the harsh and ever-changing conditions of the open sea. His marine chronometer was the culmination of years of painstaking engineering and experimentation. Harrison's marine chronometer was a mechanical marvel, a compact timekeeping device designed to withstand the rigors of sea voyages. It incorporated a balance wheel and hairspring escapement, which regulated the motion of the clockwork with incredible precision. The key innovation lay in the use of materials that minimized the effects of temperature, humidity, and motion, all of which could perturb the clock's operation. The marine chronometer revolutionized maritime navigation. It allowed sailors to measure the time difference between the ship's local time, as determined by celestial observations, and the time at a known reference point, such as the Greenwich Observatory in England. By comparing these times, navigators could calculate their longitudinal position accurately and plot their course with unprecedented precision. Harrison's invention was not only a triumph of engineering but also a testament to human determination and ingenuity. It revolutionized long-distance sea travel, enabling safer and more efficient exploration of the world's oceans. The marine chronometer played a pivotal role in the success of expeditions, from Captain James Cook's voyages to chart the Pacific Ocean to the search for the Northwest Passage. In essence, John Harrison's marine chronometer was a game-changer in the world of navigation, allowing sailors to conquer the seas with newfound confidence and accuracy. His innovative engineering achievement not only advanced the science of timekeeping but also opened up new horizons for exploration and trade, shaping the course of history and inspiring generations of engineers and scientists to come. The marine chronometer remains an enduring symbol of precision engineering and the indomitable spirit of human discovery. The mid-20th century saw the advent of quartz clocks, which revolutionized timekeeping. Quartz crystals vibrate at a consistent frequency when subjected to an electric current, and this principle, harnessed through microelectronics, became the basis for highly accurate and affordable clocks. The precision of quartz clocks even led to the development of quartz wristwatches, shrinking clock engineering to a miniature scale. The mid-20th century ushered in a significant revolution in the field of timekeeping with the advent of quartz clocks. This breakthrough was made possible by harnessing the unique properties of quartz crystals. Quartz is a naturally occurring mineral that exhibits piezoelectricity, meaning it generates a voltage when subjected to mechanical stress. Conversely, when an electric current is applied to a quartz crystal, it vibrates at an incredibly stable and precise frequency. This natural property of quartz was the key to the unparalleled accuracy of quartz clocks. Quartz clocks work by incorporating a tiny piece of quartz crystal, often cut into the shape of a tuning fork, into an electronic circuit. When an electrical current is passed through the crystal, it begins to oscillate or vibrate at a specific frequency, usually in the range of thousands of vibrations per second. These vibrations serve as the heartbeat of the clock, creating a stable and predictable timekeeping reference. The real engineering marvel behind quartz clocks lies in their ability to maintain this precise vibration frequency over extended periods. The oscillations of a quartz crystal are affected very minimally by factors like temperature, pressure, or humidity, making them exceptionally reliable. This predictability allows quartz clocks to keep time with an accuracy of just a few seconds per month, a level of precision that was unparalleled at the time of their invention. Furthermore, the miniaturization of electronic components in the mid-20th century, driven by advances in microelectronics, paved the way for the creation of compact and affordable quartz clocks. The integration of these components allowed for the mass production of quartz timekeeping devices, making accurate timekeeping accessible to people worldwide. It's worth noting that this technological leap also led to the development of quartz wristwatches, transforming the way we wear and interact with timepieces. In summary, the introduction of quartz clocks represented a pivotal moment in the history of timekeeping and clock engineering. These clocks not only revolutionized the precision and affordability of timekeeping but also enabled the creation of portable and wearable timepieces that have become iconic fashion accessories. The marriage of natural quartz properties with precision engineering and microelectronics ushered in an era where accurate time became more than just a scientific pursuit. It became an everyday convenience for people around the world, and it continues to shape the landscape of timekeeping to this day. At the forefront of modern clock engineering are atomic clocks. These instruments employ the precise vibrations of atoms, usually cesium or rubidium, to define the second. Atomic clocks are so accurate that they can lose or gain less than a second over millions of years. They are the foundation of modern timekeeping standards, such as Coordinated Universal Time, UTC. At the forefront of modern clock engineering are atomic clocks, which represent the pinnacle of timekeeping precision. These incredible instruments rely on the fundamental and remarkably consistent vibrations of atoms to define the unit of time, the second. The two most commonly used types of atomic clocks are cesium atomic clocks and rubidium atomic clocks, both of which harness the quantum properties of atoms to achieve astounding accuracy. Cesium atomic clocks operate by measuring the vibrations of cesium atoms as they transition between two energy states. This transition occurs at an astonishingly stable frequency of 9,192,631,770 Hz, which serves as the basis for defining the second. The precision achieved by cesium atomic clocks is truly awe-inspiring. These clocks can measure time intervals with an accuracy of 1 second in 30 million years, making them the gold standard for timekeeping. Rubidium atomic clocks operate on a similar principle, using the vibrations of rubidium atoms to define time. While slightly less accurate than cesium atomic clocks, rubidium clocks are still incredibly precise, with an accuracy of 1 second in several million years. Due to their smaller size and lower power requirements, Rubidium atomic clocks are often used in applications where portability and energy efficiency are crucial. The importance of atomic clocks in modern society cannot be overstated. They are the foundation of timekeeping standards, such as Coordinated Universal Time, UTC, which synchronizes time across the world with incredible accuracy. UTC is essential for various critical applications, including global navigation systems like the Global Positioning System, GPS, telecommunications, financial transactions, and scientific research. Moreover, atomic clocks play a crucial role in verifying the principles of the theory of relativity. Einstein's theory predicts that time passes more slowly in strong gravitational fields and at high velocities. Atomic clocks on satellites in the GPS constellation experience both effects, and their precise measurements provide empirical evidence for the validity of Einstein's theory. Atomic clocks are a testament to the remarkable achievements of modern clock engineering. They harness the quantum properties of atoms to define time with unparalleled precision, allowing us to synchronize our world and conduct scientific experiments that probe the very nature of our universe. As we continue to push the boundaries of scientific discovery and technological advancement, atomic clocks remain a cornerstone of our quest for ever more precise measurements of time. Clock engineering extends beyond timekeeping for personal use. The Global Positioning System relies on synchronized atomic clocks on satellites to determine accurate positions on Earth. The precision of these clocks is essential for the functionality of GPS in various applications, from navigation to telecommunications. Beyond personal timekeeping, GPS stands as one of the most transformative technologies of the modern era, and at its heart are atomic clocks that facilitate precise positioning, navigation, and a myriad of other applications. The Global Positioning System, a constellation of orbiting satellites, works by triangulating signals from these satellites to determine the receiver's location on Earth's surface. Each GPS satellite is equipped with multiple atomic clocks, usually cesium or rubidium-based, that are painstakingly synchronized with ground-based atomic clocks. The precision of these satellite clocks is astonishing, with some atomic clocks losing or gaining just a fraction of a billionth of a second per day. The role of atomic clocks in GPS is nothing short of paramount. The accuracy and synchronization of these clocks are critical for calculating the precise distances between the receiver and multiple satellites. By analyzing the time it takes for signals to travel from the satellites to the receiver, GPS receivers can determine their own position with remarkable accuracy, often down to a few meters or even centimeters. This precision is essential for a wide range of applications beyond mere map navigation. In addition to personal navigation, the impact of GPS extends to sectors like transportation, agriculture, surveying, disaster management, and telecommunications. Autonomous vehicles rely on GPS for accurate positioning, making split-second decisions based on real-time location data. Farmers use GPS-guided tractors to optimize planting and harvesting, conserving resources and increasing yields. Surveyors use GPS for precise land measurements, construction projects, and mapping. During disasters, GPS helps in coordinating rescue and relief efforts, ensuring that aid reaches those in need efficiently. Furthermore, the telecommunications industry relies on GPS for network synchronization. Accurate timekeeping is crucial for the functioning of cellular networks, ensuring that data packets are transmitted precisely when they should be. This synchronization enables seamless communication across vast distances and contributes to the reliability of modern telecommunications infrastructure. In summary, the role of atomic clocks in GPS exemplifies the profound impact that precise timekeeping and clock engineering have on our contemporary world. Beyond personal time management, the precision and synchronization of atomic clocks in GPS are indispensable for a diverse array of applications that shape our daily lives and drive progress in numerous industries. It underscores the interconnectedness of science, technology, and engineering, showcasing how innovations in one field can revolutionize and enhance many others, ultimately making our world more efficient, interconnected, and navigable. Clocks, throughout their evolution, have been more than just instruments to mark the passing of time. They have been instruments of social order, facilitating the coordination of activities, commerce, and transportation. The accuracy of clocks allowed societies to synchronize their efforts, leading to increased efficiency and productivity. This synchronization was particularly vital during the Industrial Revolution, where factory workers relied on the precise timing of shifts and production processes. In this way, clocks became the heartbeat of industrialization, guiding humanity through an era of unprecedented change. Clocks have also played an indispensable role in scientific progress. The accuracy of time measurement has been crucial in fields like astronomy, physics, and chemistry. Astronomers used precise clocks to track the movement of celestial bodies, leading to groundbreaking discoveries about the nature of our universe. In the realm of physics, Einstein's theory of relativity would not have been possible without extremely accurate timekeeping, which revealed the effects of time dilation and the constancy of the speed of light. In the world of navigation, clocks became indispensable tools for explorers and seafarers. The quest for accurate timekeeping at sea led to the development of chronometers, ensuring that ships could determine their longitude accurately. This breakthrough not only revolutionized maritime navigation but also opened new frontiers of exploration, ultimately shaping the map of the world. Fast forward to the present day, and clocks continue to be pivotal in our increasingly interconnected and globalized world. The precision of atomic clocks is at the heart of modern communication networks, ensuring that data transmission and synchronization happen seamlessly across vast distances. They are the backbone of the internet, global financial systems, and even our daily use of smartphones and GPS devices. The ability to coordinate events, from international meetings to financial transactions, relies on the accuracy of these timekeeping mechanisms. In conclusion, clocks are not merely utilitarian devices, they're a testament to human ingenuity and our unrelenting quest for precision and understanding. They have left an indelible mark on every aspect of our lives, from the way we work and communicate to how we explore the cosmos. The engineering behind clocks has evolved alongside our civilization, shaping and reflecting our pursuit of knowledge, order, and progress. So, the next time you glance at a clock, whether it's a traditional timepiece or the digital display of a smartphone, take a moment to appreciate the incredible engineering and the profound impact this simple yet remarkable device has had on our world. It is a legacy of centuries of human innovation and the embodiment of our enduring fascination with the concept of time itself.